This is not smoke, and this isn't a smokestack, at least not the kind we normally think of. It serves a totally different purpose at a power plant than smokestacks, whose job is moving combustion products high into the air, allowing them to disperse away from populated spaces. Maybe you already knew that, or at least suspected it. After all, you saw the title of this video. Plus, this kind of tower is commonly associated with nuclear plants that don't combust anything at all to create the heat that drives their generators. But that heat is the key. The largest class of power plants, called thermal power stations, use steam turbines, or turbines depending on how you say it. But once that steam makes it through the turbine, it needs to be condensed back into liquid water. It's kind of frustrating. You spend all those resources heating the water up, and then you spend even more resources to cool it back down. And a power plant isn't much good if all the electricity it generates gets used up just trying to cool that steam back down. So engineers have come up with some pretty creative ways to cool huge amounts of water, like millions of gallons or tens of thousands of cubic meters per hour, and do it relatively efficiently. Not all cooling towers look like this, but there are some really clever reasons for that iconic shape we all recognize, and I'm going to build one in the garage to show you how they work. I'm Grady, and this is Practical Engineering. Power plants could just vent steam into the atmosphere, but generally, they don't do that. For one, it wouldn't be good for the environment. The heat, moisture, and noise would affect wildlife and weather. For two, it would waste a lot of water. The feed water for a boiler is often carefully treated to avoid corrosion and mineral buildup in the machinery. It's expensive water, so it doesn't make sense to set it free. And for three, it would waste a lot of energy. It's generally less expensive to cool the steam down just enough to condense it back into liquid water so it can be reused as feed water. But even that is an enormous challenge. I talked a little bit about how power plants actually consume a lot of energy in a previous video. It's a net positive, of course, but any energy you spend on all the industrial processes required to produce electricity at scale is energy not being sent out to the grid, and that includes cooling. So engineers want to do it efficiently. One simple option is to use a cooler stream of water that already exists, like a river, lake, or sea. And in fact, there are a lot of power plants near me that do exactly that. This plant draws water from the lake on the south side, sends it through condensers, and then releases it into a channel where it flows to the north side of the lake. The slow circulation gives that water time to cool down before it reaches the plant again. But it's not feasible to have a lake or river for cooling water at every thermal power plant, and there are a lot of environmental impacts with the heat and intakes that require careful consideration. So instead, lots of power plants use cooling towers. You might be familiar with the various machines humans have devised for cooling stuff down. You might even be enjoying the comfort of such a device right this very minute. But like I mentioned, the simplest way to cool something is to simply let natural physical processes do the work. Just wait for entropy to do its thing. After all, the temperature is usually less than boiling outside, so the heat from steam will naturally transfer to the ambient air if you let it. So that's what many cooling towers do. Kind of. I designed a cooling tower in my garage so I can show you exactly how this works. This is made from laser-cut strips of acrylic with a carefully selected shape. And when I carefully tape these carefully sized strips together, I get a nice, somewhat transparent cooling tower. This is a model of a natural draft tower. It's not the most common type out there, but it is one of the simplest and also the most iconic and recognizable, so it's perfect for this demonstration. You may have noticed the holes I drilled in the bottom of each acrylic strip. This tower needs a way for air to get inside at the bottom. If you look closely at the real thing, you'll see something similar. They aren't continuous all the way down, but actually open around the bottom. Steam from turbines doesn't go to the cooling tower directly. Instead, there's a separate stream of water, aptly called the cooling water. The steam is condensed into liquid water in the condenser that's cooled by the cooling water, which then flows between the condenser and the tower. I'm simulating that here with a bucket of hot water and a beer brewing pump. That hot water gets pumped to sprayers inside the tower. If you know a little bit about thermodynamics, you know that we can only get this water as cool as the ambient air temperature. Heat naturally flows from hot to cold, so you can't get any more heat transfer once the water reaches the outside temperature. But if you know a little bit more about thermodynamics, you know there's a trick that can improve the performance of a system like this. And this layer of material below the sprayers is the key. This is called fill. I'm just using a dehumidifier pad, but in an actual cooling tower, the fill is usually a layer of plastic, carefully designed to maximize the surface area of the water in the system. It does this by forcing the water to either splash into tiny drops or form thin sheets as it falls downward. The goal is to expose as much surface area of the hot water as possible to the air flowing through the tower. Water drips down, air flows up. The pros call this counterflow, and it's the trick to the whole process. Actually, you can use crossflow as well, but let's jump over that rabbit hole for now. You might think the outside air has just one temperature, but to cooling professionals it has two. One we call the dry bulb temperature is what you normally encounter. That's what shows up in the weather report. It's what's on the thermometer. But air also has a wet bulb temperature. If you soak the end of a thermometer and pass it through the air, that water will evaporate. The drier the air, the more easily water evaporates. This is why it feels so much hotter when it's also humid outside. It takes energy, called latent heat, to convert water from a liquid to a gas, and that energy is absorbed from the liquid water, cooling it down. So as long as the ambient air isn't already saturated, 100% relative humidity, you can actually cool water below the dry bulb temperature using evaporation. And the lower the humidity of the air, the more evaporation can take place, so the bigger the difference in wet and dry bulb temperatures. This isn't anything revolutionary. Nature figured out evaporative cooling millions of years ago. It's why we sweat when it's hot. But using it at this scale is really impressive. And it's not the only innovation in a natural draft cooling tower. For that, I need to show you a cool graph. This is a psychrometric chart. It looks pretty intimidating. You could spend an entire college course learning about this stuff, and there are probably a few HVAC professionals groaning at the screen right now. But I just want to use it to explain a few important things about the physical and thermal properties of air. First, as the temperature of air goes up, its capacity to hold water goes up too. Kind of like hot tea can dissolve more sugar than cold tea, hot air can hold more water than cold air. Next, as air temperature goes up, its density goes down. Confusingly, the psychrometric chart actually shows specific volume, which is the inverse of air density. So as you move up in temperature, these lines slope downward. Hot air rises, most of us know that. But maybe less intuitively, it's also true for humidity. If you hold the temperature constant and just increase the amount of water in the air, its density goes down. Water molecules actually weigh less than the nitrogen or oxygen molecules in the air, so humid air is more buoyant than dry air. And this is the second key to a cooling tower: convection. The hot water transfers its heat to the air, the warm air becomes buoyant, flowing upward in the tower and drawing fresh air in through the intakes. But some of that hot water is also evaporated, removing more heat from the water and making the air even more buoyant. The process both cools the water down and creates a natural draft up through the tower, drawing in even more fresh, drier air as it does. Ignoring the pumps and minor control features, there are no moving parts. So just for the cost of spraying the water, you create this enormous natural convection in the tower, moving huge volumes of air into the bottom, up past the fill, and out at the top to reject large amounts of heat to the atmosphere. This is the smoke you sometimes see rising from a cooling tower. It's not actual smoke, it's just water vapor condensing into tiny droplets as the now saturated air mixes with the cooler outside air at the top of the stack. It's basically a cloud machine. That's why the plume is usually more visible during the winter months. I was really surprised at how well my little model tower worked. I was pumping water at about 120 Fahrenheit or 50 Celsius, and the water coming out was dropping by around 30 degrees F, 17 degrees C. That's like a perfect cup of coffee down to a lukewarm shower. The air coming out at the top was shockingly warm, and there was a lot of it. I was really surprised at how much airflow this thing could create just by spraying some hot water inside. I guess I just figured these processes wouldn't scale well because of turbulence, but I was wrong. It was both pretty good at cooling the water down and looking cool on camera. And part of the reason this looks so cool, the shape of the tower itself, is also crucial to its function. Natural draft cooling towers often feature this curved, swooping shape. The mathematicians call it a hyperboloid. You can actually make one yourself pretty easily. Put some sticks evenly spaced and connect it in a circle around the top and bottom, then twist. Actually, the fact that it can be made from straight lines makes these easier to construct. But that's not the only reason they're built this way. After all, a cylinder has straight lines too. There are some aerodynamic benefits to using a hyperboloid as a chimney. The wide base provides more area for air to flow in at the bottom. The constricted center accelerates the flow upward, and the wider top helps promote mixing of the hot, humid air with the cooler air outside. But really, these are secondary benefits. The main reason for the shape is structural. These towers are big. To get enough natural convection, you need a tall stack. The taller the tower, the more warm, humid air is contained inside, generating more buoyancy and more airflow. The largest natural draft towers are more than 650 feet or 200 meters tall, and more than 400 feet or 120 meters in diameter. And you want the walls to be as thin as possible. Less material means less cost and more area for airflow. But a really tall cylinder made of thin walls is not very strong. It's basically a big empty Coke can. But the double curvature of a hyperboloid stiffens the shell against vertical loads like the structure's own weight, and horizontal loads like the wind. You can also try this yourself. A thin piece of paper has almost no stiffness. As soon as you put a curve in it, it's much harder to bend perpendicular to the curve. And two curves are better than one. It's the Pringle factor. My model shows this pretty well too. I started out with thin, floppy strips of acrylic, but even just taped together, this tower is really strong. Using a hyperboloid can cut the structural stresses in half compared to a cylindrical tower, making structures like this more economical to build. So that's why natural draft towers use that shape. But that definitely doesn't mean this is the only kind of cooling tower. In fact, hyperboloid natural draft towers are actually pretty rare, in the same way that thermal power plants are pretty rare compared to large office buildings, hospitals, and schools that often use cooling towers as part of the HVAC system. Those towers often use mechanical draft systems, basically using fans to create airflow instead of tall stacks. I talk a little bit more about this in my book. We still call them cooling towers, even though they usually aren't too towery. And in fact, lots of power plants, refineries, and chemical plants use mechanical draft cooling towers as well. They're less dependent on ambient conditions to create the necessary airflow. They're smaller, usually less expensive to build, and offer some flexibility if heat loads fluctuate. And not all cooling towers use evaporative methods. Dry cooling towers just use heat exchangers inside with the cooling water flowing in a closed loop. In dry systems, you're limited by the higher dry bulb temperature instead of wet bulb, but you don't lose any water to evaporation, and you don't have to deal with the buildup of minerals that happens in wet systems as cooling water evaporates away. The reason you see big natural draft towers at power plants has everything to do with scale. The long-term savings of not having to run big fans and maintain all the associated equipment outweigh the higher initial costs. Particularly at nuclear plants built with design lives of 50 years or more, you can amortize the cost over a longer duration. Also, these facilities are usually already built in more remote locations where land is cheaper and height restrictions are less stringent, making it feasible to build such massive structures just for cooling. And they're particularly common at nuclear plants for two reasons. Number one is reliability. Cooling is an essential part of safety at a nuclear power plant. The fewer parts of a cooling system, like fans, that can go wrong in an emergency, the better. Number two is variability, or the lack of it. Nuclear facilities are usually baseload plants. Most of them run nearly non-stop at a constant output, so they can get away with a system that's designed for a single heat load rather than mechanical cooling required to ramp up or down. But even if the heat load doesn't change at large baseload plants, the weather does, and not every climate is ideal for natural draft towers. If you live in a dry place, you might be familiar with evaporative appliances that can cool and humidify the air. We called them swamp boxes when I was growing up. It makes sense that these work better in dry climates. There's less moisture in the ambient air, so you get more evaporation and thus more cooling potential. So you might assume that natural draft towers work best in areas with low relative humidity, but that's not necessarily the case, and this took me a little bit to wrap my head around. Let's look back at that psychrometric chart. Say we're in an area with a wet bulb temperature of 20 Celsius, 70 Fahrenheit. The water from our condenser comes in at 40 C, 100 F, so the air leaving the tower will be saturated at that temperature. and we're trying to cool the water down to 30°C, 85°F. If the ambient relative humidity is, say, 20%, our air is starting out here and going here. But it doesn't go in a straight line. Since the air is coming in from the bottom, it's not coming into contact with the warm water but the coldest water first. So it actually heads toward the outlet temperature and gradually veers toward the water inlet temperature as it rises through the fill. If you look at the lines for specific volume, you might see the problem. In the first part of the curve, the state of the air is moving parallel to the lines. In other words, it's not gaining any buoyancy. It's not going to rise up the stack. It might work right at startup, but as the water cools down, the airflow in the tower will slow down and stall, and you won't be able to cool the water enough. But watch what happens if you increase the relative humidity of the ambient air to 50%. The line still curves initially toward the outlet temperature before heading to the inlet temperature as it moves through the fill, but it decreases in density consistently along its entire path through the fill. So cooling engineers say that for a given wet bulb temperature, you get a better draft as relative humidity goes up. It seems counterintuitive, but another way to look at it makes more sense. Natural draft cooling towers just don't work well in hot climates. Even if the air is dry enough to evaporate a lot of water and create a lot of cooling, you just can't get it to rise up a tower on its own. So if you pay attention, you'll notice different types of cooling depending on where you are. There are 2 nuclear plants in Texas and both use reservoirs for cooling. That gives you a sense of the cost involved in cooling feed water at a power plant. In both cases, it was cheaper to build and maintain a dam and a huge lake than a cooling tower that would work well in our climate. I know that's a little bit in the weeds, but I think it's so fascinating how much engineering goes into things like this, and I've just barely scratched the surface here. The economics of building large facilities like thermal power stations require that we know for sure that each design is going to work before any construction starts. And that's driven a huge variety of types and styles of cooling towers. Engineers mix and match designs and styles according to what will work most efficiently for each application. So there's practically no end to the designs you can spot if you keep an eye out. And actually, some newer cooling towers do put flue gas into the airstream, making the tower do double duty. So I kinda lied at the beginning of the video. Depending on the tower you're looking at, there really might be some smoke in that plume coming from the top. But mostly it's just water, and in a world full of straight lines and right angles, I love that every once in a while it just makes good engineering sense to use curvy shapes to accomplish a really important job. Another place where engineering meets nice smooth shapes is underwater. If you've watched this channel, you know how much I love to learn about the various ways we interact with water. One of my favorite channels, Neo, recently released a video about the failed attempt to salvage a huge piece of the Titanic from the bottom of the ocean, and the fascinating engineering involved in the project. As always, the 3D graphic recreations are beautiful, but maybe my favorite part is the way he addresses the complicated issues surrounding the commercialization of a disaster. And if you want to check it out, it's available right now on Nebula. You've heard me talk about Nebula before. It's a streaming service built by and for independent creators, including a lot of my favorites like Neo, Wendover Productions, The Coding Train, and Branch Education. I don't know about you, but independently produced content is most of what I watch these days. I just like the authenticity and thoughtfulness of videos that haven't been through a writer's room and 10 levels of studio executives. Someone said that Nebula's like Netflix for people who love trains, and I like that comparison not just because I love trains. Nebula's totally ad-free with tons of excellent channels and lots of original series and specials like Neo's video on the Titanic. It's also a great gift, especially because a yearly membership is 40% off at the link in the description. My videos go live on Nebula before they come out on YouTube. If you're with me that independent creators are the future of great video, I hope you'll consider subscribing. That's go.nebula.tv/practicalengineering. Thank you for watching, and let me know what you think.